Hello, my name is Vincent and welcome to this session about tools and how to analyze the scheduling behavior and its impact on the goal management. During this session, we will mainly discuss on two tools. The first one is the workflow generator tools, which is let's say an enhancement on the LT app tools for those who are working on these tools. And we'll speak also about the idlestat, which let's say, gathers some state daily state statistic and a trace and a use case. So we have started all this activity on workflow generator to an idlestat just to in an answer to some complaint on the MyDate scheduler planner that was asking for a simple way to test an exercise of a change in the scheduler, and mainly to be able to do that without any, let's say, dependency with any kind of distribution or Android framework and so on. And his primary goal was to be able to emulate some workflow, some use case that was important for us, so the embedded guide, which was quite different from all the benchmark that we were using when testing the scheduler. So most of the benchmark that are used to exercise the scheduler and all the change are some heavy workflow benchmark. They just want to fill all the CPU with a lot of things to do. Whereas we are more interesting to, let's say, to exercise the scheduler when we are in a middle or low CPU load use case, when some CPU are idle, and we want to check if we are selecting the best CPU. So during this session, we will start to speak about the workload and how to simulate this workload with the RTF. So we'll go through how to describe a use case, which kind of figure we can extract. And then we will speak about idlestat, which gather a lot of statistics around the power management. And we'll finish with the limitation of the tools because we have the next step for these tools. So yeah, so as I explained, what we want is to improve the scheduler energy efficiency, and what maintainer want is to validate that the patch we send on the mailing list effectively do what we are saying. So yeah, so as there were lack on this kind of workflow generator tools, we have started the workflow generator tools, to emulate so mainly the mid and low use case, and also to emulate all kind of streaming use case, which is something, as far as I can tell, I don't know any benchmark that can emulate some kind of streaming use case without any dependency with some real, let's say, audio playback, middleware, and so on. And we also want to make this tool quite simple to use, to compile, and to put on a distribution. We don't want a lot of dependency with middleware framework and so on. So, how to simulate the workload? So right now with RTF, everything is based on a JSON file. So you use this JSON file to describe the behavior of each task and which kind of resources you're going to use to make the synchronization between these tasks. So, and also, yeah, how long you want to run your use case and which kind of statistic you want to have. So this JSON file is mainly based on three JSON object, one which is called the global section, another one which is the task section, and the last one is the resources. So let's start with the first one, which is the global object. The global object is mainly used to describe, let's say, the main behaviors. The duration, if you want to generate some F-trace event, if you want to get some statistic and generate some plots, and a lot of additional things. One interesting thing in this global object is the calibration parameter. So what we want to emulate is a workload that will scale with the frequency change, with the microarchitecture on which is working on. So for that, we can't simply use, so when we want to run, let's say, in a use case where you have a workload that you need to run 5 milliseconds and sleep 5 milliseconds, the 5 milliseconds only makes sense at one frequency on one architecture. But if this task migrates on another core, or if the frequency change, your workload must scale with this change, just to reflect the reality. So what we have decided to do is to use a log loop to emulate the run activity. So we just translate this runtime in a number of loops. So we must calibrate on the platform how long the loop is. So before starting a use case, we are calibrating the use case for the platform. So we are running the simple calibration algorithm that will evaluate how long one loop is on this core. And based on that, all the run duration will be translated in a number of loops. So what will happen is that the 5 millisecond run will effectively run 5 milliseconds if you want max frequency on the CPU that has been used for the calibration. But if your system decides to slow down the frequency, the runtime will be longer, which is normal, which is the normal behavior on the system. Another interesting thing is that sometimes you don't want to go to this calibration step. If you already know the loop, the duration of a loop on your platform, you can just keep, and instead of setting calibrate the system on CPU 0, you can just say, okay, the calibration on this platform, I already know that. Skip the calibration step and use these values that will be the number of nanoseconds per loop.
So what's the use of that feature? Why not just let it figure out at runtime?
Yes. Save. The goal is to save. There is several interesting things that if you want to save time, so if you have to do 100 use cases.
How much time are we talking about? Seconds?
Yes. Maybe that's a 1 to 2 seconds. It depends. It depends on how we reach this max state.
Maybe you want to check whether the tool is robust enough to work with an incorrect expression.
I guess the other thing is that presumably when you're calibrating, you can set what the initial state is. So you can say I'm going to calibrate at max OPB on one CPU. Whereas when you do the run, you'll be at a particular OPB. So perhaps doing the calibration step there would not make sense.
And another point is that if you have a use case, you run on a platform, the calibration, then if you run the same use case on another platform, if you recalibrate, so let's say you have a platform with a 87 at 1 gig max frequency, you have a use case that emulate the reality with the duration and so on. If you move that use case on a platform with the A15 at 2 gig, the 5 milliseconds doesn't make sense. You should be shorter compared to the other platform. So if you want to test or to compare across platform, you must use the same load. So you must use the same value.
So you won't artificially create the wrong scenario over there.
Yeah. Otherwise, whatever you're using on A7 on one platform or A15 on another one, you will run 5 milliseconds, which doesn't reflect reality. So yeah, there is also a lot of feature and parameters that you can set. So the documentation right now is not at a so good level, but we have planned to improve that to describe all the parameters that can be done. But the default value for the month is quite enough for starting, and then the easiest way to understand is to test with different parameters. The other point is so the resource description. So the standard object is the resource description. In order to be as real as possible, yes. Another thing that was lacking in other benchmarks is to create this dependency between threads. So in our use case, most of the time we have one thread or one interrupt that will wake up another one, that will wake up another one, and then come back and so on. All these dependency make a real difference in the scheduling behavior. So just starting or waking up a thread without the dependency with another one will not give you the same result as I'm in a thread that will wake up another one, because the scheduler will take a quite different decision. So we want to emulate this dependency between threads, which make difference at the end in the behavior. So you can describe. You have to declare all these resources just for a matter of allocating memory for that and setting that. So the resources are quite simple. So among the resources, you have the run and sleep resources, which are so obvious that you don't have to declare that. And then you have some kind of timer, mutex, signal, wait, and broadcast resources, which are the main interaction you can find between thread and user space. So the mutex is just if you want to emulate two threads accessing to a critical resources simultaneously. So in some cases you will have to wait the other one. Or if you have one thread that needs to be synced with another one, you can use the signal, wait, and broadcast the thread library. The timer, I will come back on that a bit later. It's, let's say, it's a special sleep resources. So maybe I can just speak that right now. So when you describe a use case for a thread, you say, okay, I want to run for an amount of time, I want to sleep for an amount of time. And by default, the sleep duration will, so if you say I want to sleep 5 milliseconds, you will start this 5 milliseconds sleep after the runtime. If your runtime will take more time because of scheduling aspect, because of frequency scaling, the period of your pattern will not be 5 and 5, but that will be 6 milliseconds and 5 milliseconds. So your period will be no more 10 milliseconds, but 11. It will depend on the scheduling and frequency scaling. In some use case, in streaming aspect, we have a wake-up tick that wakes up us each 10 milliseconds, whatever the duration of the run is, because most of the time we have an hardware decoder or something like that, or PCM IP that will just fire an interrupt to say, fill my buffer, and then you have 10 milliseconds to do that, whatever. So the timer is just a way to be sure that you will be wake up 10 milliseconds, each 10 milliseconds, or each whatever the number of milliseconds you want, without any dependency of the duration of the previous event for your thread. That's quite useful to emulate, for example, an MP3 playback in which you have this periodic wake up based on the PCM buffer sizes. Yeah, and so then the task. So the last JSON object is a task. It's the task object in which we describe the behavior of all your tasks. We have tried to make that as simple as possible. So you have some general characteristics like the priority, so you can set the scheduler class you want to use, the priority, the CPU affinity. You can specify how many time you want to run. So you will. The goal is that you will describe a pattern, so a list of events to run. And you can describe how many times you want to run this sequence. And you can also describe several sequences and say, I want to run this kind of behavior for 3 times, then change my behavior to use that for 3 times, then come back to the other. The goal is to create some not so periodic behavior. Like, for example, during web browser, you can see different kind of steps. You have some startup rendering, then some large computing, then coming back to rendering or scrolling. The behavior is not always the same. We have some periodic pattern, but not always the same one. So that's why we have as we have this phase object that will describe the behavior of the task. So this phase object can be made of several sub-behavior. So phase 1, phase 2, and so on. And in each phase, you will describe how long you want to run, if you want to lock up a mutex, if you want to wake up another one, another thread, and so on, how many times you want to run this phase. But because we want to keep that simple, most of use case, your thread will have only one behavior, one simple run sleep signal sequence. So you can just keep all the phase and P1 object, and in your thread you just have to say the priority. If you have to change the priority, the number of loops, so -1 just to say loop indefinitely, and then just describe your sequence, run for a number of times, sleep for a number of times, and that's all. The phase object are only necessary if you want to create more complex behavior. Otherwise, you just have to skip that and describe the sequence. We have one, let's say, limitation or one constraint, which is an object, is that all the object or sub-object must have a unique key. So when you are describing a sequence for task, we use the K with a special, let's say, prefix. So if you want to run, you will say, in the JSON K, you will say run, and then the duration. If you want to sleep, you will say sleep and the duration. If you want to signal, you will say signal and which signal you want to trigger, and so on. But because each K must be unique, you must use, let's say, a unique ID behind this action. In order to solve this issue, we have added a script so that you can simply say run for a number of times, sleep for a number of times, signal this, or log this mutex, and so on. And you can just use this script that will add this unique ID at the end of the action, just to prevent you to be sure that you use one unique ID. If you don't have unique ID, the JSON will just remove all the duplicated action. That's why. So we have some statistics also, because even if our primary target is to get some power figures without any kind of performance figures, that doesn't make really sense, because you can be in a situation where you will run 3 times more loop with one patchet without this patchet. So you can have a higher power consumption, but just because you have run much more things. So you must use the power consumption figure with some kind of performance figure. That can be, yeah.
Can you define? Thank you. Can you define a load percentage?
No, not now.
So you have to deduce that directly from the duration, the load and the duration, and
yeah. Just because, in fact, so I think we discussed that. What the load percentage is. Behind the load percentage, let's say you want 10%, but 10% for which period? So in fact, you still have to set 2 values, the percentage and what will be the period, the duty cycle. So at the end, we prefer just to set the runtime and the sleep time, which is obviously the same. You will not save any parameter by setting a percentage. Only a computation. When you, let's say, when you will do that.
Okay, so it's up to the user to deduce this percentage depending on the load and the sleep duration.
If you want, because 10% of load can be 1 millisecond run each 9 milliseconds, or 10 milliseconds each 90 milliseconds. And the behavior is quite different than here. That's why. Only percentage doesn't make sense if you don't have the period. Because yes, the behavior with the scheduler is quite different. That's why.
Okay, thanks.
So we have three main statistics in order to evaluate the performance of the use case. So for each thread and for each run of the sequence, we have the load, the run duration, and the period duration. The load is the number of times you have run the loop, which in our I think it's not really readable there. But there I have put a statistic of one thread of the MP3 use case that we have run with RTI. So in the MP3 use case, we always have the same load for each loop because we have always the same amount of things to do. But we can see that the run duration is not always the same. It's just changing between the minimum green.
That's a green.
Yes, that's a green one, which is not really readable there. So we are just moving between 5 and 7 milliseconds, which mainly depends on the frequency at which you have run and if you have been preempted by another task. And the last one is the period duration. So it's the time to run to execute a full sequence. The runtime, but also all the sleep and the wait for another task to wake up to, all the new text lock and so on. That can give you the main interest of that is for streaming use case. You can see if you miss a deadline. For example, for MP3 playback, you know that you have to fill your PCM buffer each 30 milliseconds. And if for one reason take more than 30 milliseconds to run this sequence, you have missed the deadline and you will hear something on the Excel. So we have the load, which is the amount of work we have emulated. We have the run duration, so the amount of time to execute this load, and we have the period, so the amount of time to run everything, the full sequence. So that you can, with that you can evaluate, or you can check that the run duration of a loop have never be longer than the deadline, and you can be sure that you have run an enough amount of load, and so on, so that you can compare that with some power figures. So this is the trace of the MP3 JSON use case, which is based on, I think it's a TC2 trace. It's based on a thread that was sent by Morton, in which was described in several uses, among which the MP3 player. So we can see this periodic activity with one main thread that wakes up the other one. We have some sync between threads. So yeah, you can set the name thread just to make that easier to see. So in the JSON file, what we have done is that we are creating this periodic which simulates an hardware wake up. So you have to run, let's say on most of use cases, you have to run on CPU 0, and I think it's 6 milliseconds in this use case. Each 6 milliseconds each wake up, but only once every 6 wake up, it will wake up the thread that will fill the buffer. That's the use case. So we are relating this periodic wake up, and once each 6 wake up the main thread. And so we have this sync with the signal, and this main thread will wake up another one. Here we have this created, this let's say, We have one thread that just asks another one to do a job and wait from here. All this sync event is also possible with the tools.
This is trying to emulate the Android MP3 playback use case, by the way. So we've basically captured the process and tried to emulate that artificial.
So yeah, so we have the audio. So we have the audio out, which is, I think, the main goal of this thread is to build the PCM buffer. We have the audio track and the MP3 decoder part, and the raw mix callback, and that's what will be done there. Not in detail. So, if you have some question about LTR, about details about behavior, don't hesitate. Otherwise, we will go and speak about idlestat. We'll come a bit later on the limitation and the next in the future of the tools.
Yeah, I mean, so to recap, RTF was created, or the extensions to RTF were created to allow us to emulate loads so that upstream maintainers can run them on their desktops without having to run an Android environment or something like that. And the goal, currently we have MP3 and browser use cases being emulated in the examples directory. There's a Git tree at the end of the slide deck. The plan is to add some more workloads in there to emulate. The final goal being that we started with the mobile workloads because that was the main focus. Most of the scheduler testing that happens today is around enterprise workloads. And so the scheduler maintainers basically told us, you tell us what mobile workloads look like. And so that's what we're trying to provide them.
So you actually have 3 use cases ready. Because you can do composite ones as well.
Yeah.
But there's a composition one.
Yes. You can merge.
Because that's nice representation. The benchmark audio is pretty awesome.
Just a second.
Sorry, what I was saying was that you actually have 3 use cases, because if you've done browser and with some pattern in mind, and if you've done audio, then you by definition have browser and audio, which is on which we do a lot of analysis.
Yeah. Well, one ultimate goal would be to be able to extract a JSON.
Yes.
That would be not simple, but our ultimate goal would be you record the tracks for a use case, and then we have a tool that will extract all this periodic activity and create a JSON file. But that's simple things.
The complexity of the
yeah,
but I think
because you have to extract
this
this periodic activity, you have to remove this old noise that doesn't have to do with your use case.
and dependencies. So
Yeah.
not in that straightforward model.
So how does all of this connect back to power management? We're working on the energy-aware scheduler project. Scheduler maintainers first want to be able to know what kind of workloads we are interested in, and then they want to be able to evaluate the changes that these patches are making to the scheduling behavior. Currently, there are some tools like SchedStat, which tell you something about what's happening in the scheduling. But from a power management perspective, we didn't have anything which gave us some insight into what happened as a result of this patch. Did we increase residency times in an idle state or at a particular operating point, or did we make things worse? It wasn't easy to say. I mean, there are things, tools like PowerTalk, but the interactive nature of PowerTalk makes it hard to do post-processing, really. So idlestat was created as a, to fill in that gap. It's basically designed around, the basic design principles were to be as low cost as possible in terms of gathering all of that data. So it uses ftrace to gather all the C state, B state events, wake ups, and also to so being low cost was the number one, and then being able to post process all that data. That was one of the other design goals. We know today that the scheduler, CPU free, CPU idle currently not coordinated, and that's what the energy aware scheduler is trying to fix by merging all of that code into the scheduler and letting the scheduler handle these CPU states. So in a sense, knowing the C state and B state behavior and tracking the changes in B state and C state behavior is an indication of whether we have improved or regressed things as far as power management is concerned. So it's just one vector, so it's not the only vector. There's obviously other statistics around caches and migrations and whatnot, but it is one statistic into that is of particular interest to us. So at the moment, idlestat tracks that one statistic, which is C states, B states, and wake ups. What changes when you apply a certain branch? So we did a simple example here. So this is on a Chromebook running a mainline kernel. We literally did this last week. It's not optimized at all. So we turned off. So Chromebook 2 has an octa-core Exynos. We turned off 4 of the cores. So it only runs on the 4 cores based on Kevin's mainline tree, and the MP3 use case that Hassan just described earlier. And what we are comparing is basically the behavior between schedmc. There's a kconfig option, schedmc. So we turn it on or off, and we wanted to just show you what idlestat can tell us from there. So we have to get out of the slide. Okay, so this is actually the report that idlestat will produce for you. We've actually put it in a meld diff, so you can see what happens on both sides. So this was on use case 1. So this is with schedmc off, and this one is with schedmc on. So you'll see here there's a cluster A. So that's CPU 0, 1, 2, 3. So that's 4 CPUs here, and you'll see what C states they went into. We have min, max, average time in those C states. The total amount of time spent in that state, the amount of times we hit that state, and then the over and under predictions. So we either over predicted our residency in that state, and we actually got woken up earlier, or we under predicted and we actually could have stayed longer. So could you scroll down?
Oh, yeah.
We'll just talk through what idlestat can show, and then we can discuss the differences. So that was the C states, and this is about B states. So again, here it's showing you that it went through all these operating points, again, min, max, average, total hits, etc., on the various CPUs. And all of this is data that we captured from ftrace. So it's not magic, it's just ftrace data being formatted into something easy to use. And at the bottom, we have the wake up statistics. So how many IPRs, which IRQs woke us up, number of times we were woken up, and things of that sort on each CPU. So this is what idlestat will tell you today. The reporting format, as it is, I don't think is frozen. We could do a lot better. So we are hoping for some discussion around that after the presentation on how we could improve this data. If you go back out to the C state data, there's some things in there which are interesting. So it's a cluster state. So if you see C0, C1, C2, C3, we have these separate states for each of them, WFI, C1, how much time. And then there is this cluster C state. So this is being calculated by idlestat. So what it does is basically takes an intersection. It already knows that C0, C1, C2, C3 are part of the same domain, and so it does an intersection and says if all these CPUs were in a certain state, in this case C1, then the entire cluster would have gone into that state. So if you see here, you look at the total amount of time spent in that state for that cluster. So just with scale MC off and on, You spend about 2.44 seconds here with off, and here it got reduced to 683 milliseconds. This is because SCADMC on basically tries to spread out your tasks, because it tries to use the shared resource flag being set by the scheduler. So this is something very easy that you could make out here. There were some other interesting things we saw. Here. This information here. So if you look at the total amount of time spent in WF5 on CPU3 here with SCADMC off, it was 45 milliseconds in WF5, and for some reason we spent 3 seconds in WF5 here. And we were trying to analyze what the hell was happening there. It seems like menu governor does a lousy job of predicting. When we could have actually gone to a C1 state much longer, it kept us in WF5. So we have some traces there. You want to talk through this? Sorry? You want to talk through this?
Take a mic. Or you can, so this one is with SCADMC off. So you can see how the tasks are distributed. So just SCADMC config, just to explain what it is. The only difference with SCADMC is to enable the topology awareness in the scheduler for your platform, for your architecture. So when SCADMC is off for ARM architecture, all the CPU, so you don't use the topology information, and all the CPU are seen as independent CPU without cache sharing and so on. When you enable SCADMC, the only difference for the ARM architecture is that all the CPU in one cluster will have a flag to say we share our cache. That's the only difference. Just one flag to say we share our cache or we don't share. And this is used in the scheduler when the tasks wake up. And if the CPU on which the task wake up already run a task, is already busy with another task, it will look for another CPU that shares its cache. And it will migrate that CPU on this idle CPU, because that doesn't cost almost nothing to migrate on the same cache, let's say level. So here's the behavior of when SCADMC is off. So you will see less migration at wake up when SCADMC is off. The main disadvantage is that you can lose some throughput because you can have 2 tasks on the same CPU, whereas another CPU is idle. Yes. And so for this one, it's the same. So in this case, SCADMC is on. It's not really seeable there, but in the other one, you can see that sometimes two tasks, let's say. If you look there, you can see that here we have some tasks that are just using the same CPU at the same time, whereas other CPU is idle. Whereas in this use case, you will never see that because you will migrate the task on the idle CPU. And when you look at the trace at one time, I don't know exactly why, the audio of task migrate from CPU 1 to CPU 2. And once that happened, the CPU, so yeah, this trace has not been done simultaneously to the idlestat statistics. So in this trace, the issue is on CPU 2 and CPU 3. But it's not always happened. So we're just migrating the task, and once we are migrating the task, the menu governor always select the WF5 CPU, the WF5 state for the CPU instead of using the C1 state. It's just that by migrating the task, the menu governor we have just trashed all the menu governor statistic about how long the sleep duration is. Yes, how long the reality is compared to the predicted value, and it starts to just always selecting the WF5 state. just because maybe. So yeah, so when you look on CPU2, the default behavior is we wake up, we run for a while, a short idle, we run, and then a long idle. And by migrating the task for the menu governor, the behavior changed. We have a long run, a long sleep, a long run, a long sleep. And just because of this direct change in the behavior, the menu governor and its bucket and statistic and how it used the predicted value and how it used the timer, sleep duration, translate that in a predicted value, can just give up all the previous statistics because we have completely changed the behavior. And that what happened is that it's just selecting the wrong C state and see, okay, we will wake up in a short time, so stay in W effect, which is no more true.
Yeah, that we can go to the next.
This is WhatsApp.
So some of the limitations that we have currently. So obviously we can't actually correlate this to the hardware state on whether a cluster actually powered down. So this is the requested C state from a driver perspective. I mean, theoretically, you could correlate that by adding a DAC and actually measuring stuff along the timeline, but that's not why we've created idlestat. We don't want to, not yet anyways, we don't want to try to correlate to the hardware state yet. This is just to give the maintainers a very quick view of if anything major has changed and whether it requires investigation.
But you also did the agglomeration, like you explained earlier, about the C1 on the cluster state, right? So assuming that the platform coordinates well, you should generally get it right. So it's not a, it's a limitation understood, but it's not like the end of the world.
It's not a tool limitation anymore.
Yes, exactly. And if you took the idlestat report and someone actually did the power measurements, you could sort of try to correlate, saying, are we actually seeing this behavior?
So isn't the real problem that there is no, you're not getting a view of what the actual hardware C state transition into from the kernel, right? So in an ideal case, there would be a protocol that people would agree on. It's probably not going to happen. Worth calling out, right?
Well, you have to have some synchronization in external hardware.
This was a bait for Charles, actually. So.
Yeah, but I'm not jumping.
All right. So one of the other things is that we showed you a mail view to see what the differences were. But obviously, it's not very hard to. It's very hard to eyeball the two reports and see what actually changed. So we are soliciting some feedback on what would be a better way of taking two traces from idlestat and basically showing developers, here's a quantitative change. You have a 5% regression, 10% regression, or in your C-state residency or something like that. So if there is any ideas out there, we're looking into hear those. And then the third one is the topology data. So at the moment, you measure this on a target hardware, let's say an ARM platform, and then you want to maybe post-process this on your PC, which is running x86. It'll sort of mess up all the statistics. If we could capture all the topology data into that trace, then we would be able to post-process it in any platform. So that's something we probably get around fixing.
But you don't necessarily need the topology data in the trace, right? You could always say that express the topology data using some grammar, and then you've solved the. You just need trace from the target. It doesn't matter where you.
It's easier to just capture the topology data.
I just see the complexity out of that.
If you do that, if you don't capture this on the target, is one of my questions as well, then how would you capture? You'd also need to express the initial state. That's one of the problems with this. You need to know the initial B states, you need to know the initial C states. If you're doing everything on the target, you don't require that as part of your data capture.
I agree with the initial statement, but reality is that you're not able to get a sufficiently comprehensive view of the topology from the trace, right? And you can infer it by looking at.
Not from the trace. You could just dump SFS and make it part of your report.
Yeah, I mean, I always perceive that even the producers of that information in SysFS, like the CPU idle subsystem or CPU Freak or even the scheduler, right? It doesn't actually have the complete picture, right? So why don't you just short circuit that and say that here's the expression of the topology, and now that you have the trace, can the tool just use the tool? That way you don't have you sort of short circuit the problem.
Well, to be honest, not really, because you really want, I mean, that's what my preference would be, which would be the runtime state of the system should actually reflect what the real topology is and why certain decisions are being taken. So if some data around that is missing, then maybe we should just fix that and just capture it from there instead of creating yet another grammar to define it externally.
No, I agree. I was just, to me, it sounds like that's a larger problem and potentially unfixable, but I may be being too pessimistic.
Yeah, I mean, it's a limitation. We need to figure out what is the best way to solve it at this point. So I have to call it out. RTI.
Yeah, so
I think it's worth to mention that we want to. We want to have also the idlestat traces to be processed by TraceCMD and Canal Track. So if we merge the topology information inside, we can use these tools for that. So we have to find a way to separate both of them.
So I think today with this tool it's not possible to actually gather the trace information with trace command and then do the post-processing in idlestat, because you can run a workload with idlestat, and in the trace command output there will be some topology information which is not compatible with the trace command output, right?
So we can import trace command traces. We added that feature. Although Kevin did report about he was trying to do that, so we need to go back and look at that. But we've added the feature to import trace command.
But the topology won't be there.
Yeah,
So the cluster information will be not computed.
Okay, so in this case we don't get any cluster information.
Right.
So, but you still work on the feature that to actually deliver this topology information on the command line then, or through a means of some other config file, or I don't know.
It's possible.
Okay.
yeah, so let's move on.
We're out of time, so we need to finish up.
For LTF, we have three main limitations. The one is a cross-compilation mess, because yes, several people report that it was quite complex, and they were unable to cross-compile LTF because of all the dependencies in some Debian package. So we'll look at that in order to solve this issue to make LTF compilation quite simple with as minimum dependency as possible.
But possibly a silly question. Why do you want to cross-compile?
Why do we want to cross-compile? Because a lot of people are cross-compiling, creating your TFS. When you created all the applications.
I might have gotten this wrong, but I thought RTF, you were just meaning to sort of allow a synthetic workload that's been expressed using the RTF grammar to be replayed on the desktop, right?
Yeah.
So for the large, I mean, it's for completeness' sake, it sounds right that you want cross-compilation ability, but somebody might want to do
So yeah, I mean, LTF, you want to run LTF on any kind of platform.
True. Okay.
And for example, I have used that on just to exercise my Chromebook 2 platform. I have used that. So we want to be able to combine that for any kind of platform.
I agree. I suppose I was taking a partisan view that on the target, you're actually running the workload.
Yeah.
You're simulating the workload, not on the target. You're simulating on the desktop.
Yeah, but yeah, with your simulating just to compare with the reality.
Yeah.
So that's the other one is JSON limitation, just because of this unique key for each object and the fact that we can't include. So we are studying to move on another kind of library, YAM, is something that we have to think about for a while. We haven't changed for the moment, but maybe we'll change, which will give only benefits. And the last one is how to emulate the standard interrupt. Right now, we can only create some thread that can wake up for quite a short duration, but that's a thread, that's not really an interrupt. And because we are in user space, in order to have any dependency with the camera and so on, we can't just create an interrupt. That's not possible, right? So either we need to add some feature, we need to create some driver, I don't know what, to have some way to just create this interrupt, this in-kernel interrupt that will do nothing except of waking up the CPU without scheduling anything. Because that's, I think that's something, an important behavior of an embedded platform. You have some interrupt that do their job without waking up any thread. So from a scheduler point of view, that's just, it's non-visible, but from a power point of view, that makes a huge difference in the system selection and how we will re-enter. And so for the future, I will start with that, yeah. Come back to LCU. So the goal is to have more of a description, either real use case or some. So even, yeah, we want to emulate a real use case, but even if we have a good sequence that we think it's a stress test for the scheduler or it's a typical behavior, we want to add that. So even if people have, let's say, a real sequence or not a real sequence, an interesting sequence, even if it's not reality, but because you think it's really important that the scheduler behave correctly. This kind of sequence, we want to like that. And we also want to have more kind of load. Right now, the load loop is only CPU bounded, so we are just doing some mathematical behavior. We want to be able to select memory bandwidth load or IO bandwidth load or any kind of bandwidth, or any kind of load. And the last point is to be able to increment the load. Right now, if you want to increment the load, we must create a phase each time we want to increment. We want to be able to automatically increment the load, to say, okay, I have this run, this idle time, but I want the run to increase step by step. We are out. Yeah.
So for LCU, there is the energy model that we'd like to merge. So knowing the C states and B states, we could actually say how much energy a workload consumes. A diff mode, if there's some ideas, please come talk to us how we show the differences. Architecture specific hooks to correlate hardware state. This is going back to Intel because they can actually do that very easily. Their program buff stuff. And maybe a histogram instead of mean max average might be more useful information. So that's another thing to consider. That's it. So please come talk to us later if you have any questions.
Yeah.